Today we're going to look at recurrent neural networks. I'm going to start to give you a general idea about recurrent neural networks, and we will look at unfolding the recurrent network so that we can see it as if it was spread out in different layers instead of iterating through time. We're going to see the problem of implementing backpropagation through time. It's actually not a big problem, but there are some interesting details here. And then look at how to learn long-term dependencies. This is when we are dealing with data in sequence, in which there are relations between different parts of the sequence, but they are spread out a long time, so they are distanced from one another. And we will see several solutions to improving learning of these long-term dependencies, among which these structured or gated recurrent neural networks, which are the GRUs, the gated recurrent units, and the long short-term memory cells. So this is basically this last note is a personal feeling of mine. Recurrent neural networks are important in deep learning, and they are still being used in applications involving sequence data in sequences like time series, natural language processing, and so on. But they are not very efficient to train. This recurrency is elegant in theory, but in practice it doesn't fit very well with the hardware we have. And so if we don't use recurrency, we can train the networks much faster. And since convolutional networks and transformers, which are networks based on attention mechanisms, we will cover those next week. These also perform well in many applications where recurrent networks have been used. And since they can be trained much more efficiently, my feeling is that recurrent networks will not be as useful in the future as they have been so far. But still, this is an important part of deep learning, so I think you should have a good idea of how they work and be able to use them in practice. So I'm going to start this first part with the theory to explain how what recurrent networks are and how they work. And then after the break, we'll have a very short lecture showing you how to do this in Keras and showing you the exercise that you're going to do later. So let's start with the basic idea. The basic idea here is simple, is that we have a network architecture in which outputs are fed back into the network with a time delay. So we don't have just a feed-forward network where the input comes in and then the output goes out, but the output also feeds back into the network, and we repeat the computations. And we do this with at each time step, we pass through the network and we feed in the output of the previous time step as a new input. We can also keep feeding in new inputs from our data. So this is very good for dealing with sequential data. There are two important concepts here. One that we've been seeing so far is that when we stack nonlinear transformations, we can get more power in the representations that we are obtaining. So in this case, this stacking is done over time as we iterate through the network, for example. And also the idea of parameter sharing, like we saw in convolutional networks, where if we use the same parameters in different places, it's much easier to learn to identify patterns that can occur in different positions in our data. And the motivation here is, since we are iterating the network and using the same parameters all through a sequence of data, we can more easily find the patterns of interest anywhere where they occur in the sequence. However, we keep the state, an evolution of the state of the network as we iterate through this sequence, and so the state can remember important things about the history of the sequence of inputs so far. So recurrent neural networks are specially suited for problems dealing with sequential data. Anything that involves either processing, inputting, or outputting sequences of values recurrent neural networks is a natural way of approaching that. So let's start with a very simple network. In this case, it has no inputs. We can consider the output to be the final state there. So this would not be very interesting in practice, but it's the simplest we can write, so that we have this idea that we can look at the recurrent network as a recursive function. The state as times t is a function of the parameters that we are learning, this matrix U, which has the parameters that are involved in transforming from the previous state to the current state, and also whatever vector we had in the previous state. So this would be the recursive definition, and we can draw it like this, where the state depends on the state, but this square here indicates that we have a time delay of 1 step. So this is not an infinite instantaneous loop. It means that when we are going to compute the state at the next time step, we use the values from the previous time step and update the state. Another useful way of conceiving, of imagining this recurrent network is to unfold it and spread it out as if it was a feed-forward network. So if we share the same parameters over the different layers, we can represent this network by unfolding it like this, and it would be just a feed-forward network where we start with some state at times t minus 2, then we evolve in the next layer to time t minus 1, and so on. So instead of having the time steps, we have different layers in a feed-forward network, and we always use the same set of parameters, so we are sharing the parameters across different layers. We could do this with our recursive function by unfolding for a finite number of steps. We would just simply write this, so the state at times t is a function of the parameters and a function of the parameters and a function of the parameters all the way to times t minus 2. So we were chaining all these transformations in a sequence. So we're going to look at recurrent neural networks in this way because it's easier to imagine, to think about what is happening when we think of unfolding the time sequence of the recurrent network into a feed-forward network. So if we want to deal with sequential data, we can keep feeding inputs into the sequence, into the network, depending on the sequence that we have. So note that this would be the value corresponding to time t minus 2, t minus 1, t, and so on, and we will keep feeding new values of our sequence into the network. We have always these parameters, v, which are involved in the transformation that our network is doing from the input to the state of the network. And we also have these parameters u that are involved in changing the state from one step to the other. So this would be the actual network. We keep feeding new values of x here, and we keep iterating through time. So we only have one cell in this case, or one layer on our recurrent network. But since we keep iterating through time, this works as if were stacking multiple layers. And so we have a deep neural network, even though we are just using the same layer again and again. And one good thing about this is that we can easily process sequences of any arbitrary length. It doesn't matter if they are very long or shorter or whatever. It's just that the number of iterations we loop through is the number of values that we are feeding into the network. And at the end, we can use, for example, this final state as the output. So one good thing about recurrent networks is that they can easily transform sequences of arbitrary length into a fixed length representation. That would be just a vector of the activation of the network at the end of the loop, after looping through the whole sequence. Also, since we are sharing these parameters, we always use the same transformation from the input into the state, and also these transformations along the state, but especially this one from transforming the input into the state of the network. We can make it easier to identify patterns that do not depend on position. So basically, this set of parameters u will help us remember things that are occurring spread out in time. This set of parameters v will optimize the way we are processing different values of the input vector at different times. So using this, we can train the network to recognize parameters, recognize patterns that may occur in different places in the sequence. So in training, when you're training in Keras, you need to fix the batch size. We're going to look at this in some detail in the second part. But in general, we can use recurrent neural networks to process sequences of arbitrary length. And this is good for dealing with time series, for text processing, for audio, things like that. So everything that has sequence, whether it is really sequence over time or just a notion of sequence, something that comes before and after, we can use recurrent neural networks for that, because they have this ability of identifying patterns along the sequence, and they can easily transform sequences of arbitrary length into fixed length representation. All we need to do is look at the output at the end after looping a number of times through the sequence. We can also use recurrent neural networks to give us an output at any time step. So at each time step we get an output, and we can also have specific parameters that transform the state into the output. So this would be another architecture that we can represent this way. We keep feeding values of our sequence of inputs. This will change the state of the network, and also the state of the network changes over time. So the state of the network will remember what has been happening in the past, and then as a function of this state we output different values, also with a set of parameters that are learned that transform the state into the output. So this way we can transform one sequence of inputs into one sequence of outputs. Depending on the length of the sequence of inputs, we will have the same length in the sequence of outputs, but we can vary the length easily. It's just a difference in the number of iterations we are running through our network. So this would be another kind of problem that it's easier to solve with recurrent neural networks, where we need to convert one sequence of inputs into one sequence of outputs. If we want to train this network, then we will need a loss function and some ground truth, some target that we have for each of those outputs. So this would be a representation of that here. We are feeding inputs in sequence. This will change the state of the network and will result in different outputs. At each time step we have a new output, and if we know what the output should be for that type step, so this is the ground truth in our label data, we can use a loss function, and then we can use this to train our network. Basically what we need now to do is just backpropagate the gradients of the loss function back through the network, so that we update our parameters, our trainable parameters here, W, U, and V. We'll see a bit more about this, but this would be the idea for training this type of recurrent neural network. So basically what we need here is to have the X values in sequence, what is the sequence of values for the input, and the corresponding sequence of the ground truth for the output, so that we can do supervised training of this network. We can have different kinds of networks. So in this case, we have a hidden state here inside the network that is being used to keep track of the history of the network. One alternative would be to look at the output and use the output from the previous state as the information that will tell the network how to change to the next state. So the network is not receiving directly from the previous hidden state, but from the output. This is a bit more limiting, because note that the output is constrained by the target value for which we are training. So we cannot put anything here. We need to put something that is as close as possible to that target value. If we create a network like this, then it's we are much freer to have different state values here, feeding into the next one, and then transforming this one in the appropriate output values. If we do it like this, then the output is constrained by the need to be close to the target value, and so it cannot deliver as much information as freely to the next state. So this variant would have a poorer representation in the hidden state here than what we could achieve with this one. However, there is an advantage here. If we, instead of using the output, we use the target value for the next iteration, so this is called teacher forcing. We are using, instead of the output here in orange, that should be as close as possible to the ground truth. Instead of using this value to feed into the next state, we are going to skip this part, and instead of using the guess from the previous iteration, we use the true value that it should have gotten. So this not only improves training, because we are correcting the errors from the previous iteration. Suppose that in the first iteration our network does not guess correctly here and gets an output value that is very different from the ground truth. It's better to use the ground truth to feed into the next step instead of using the output. But if we do it like this with teacher forcing, then all of these become independent. Note that we can train this step without knowing what this one did. Or we can evaluate all the gradients of the loss function and so on for this step without knowing what this one did, because we don't need the output there. We already have the ground truth, so we can use that here. So in this case, if we have this particular network like this, we can do teacher forcing by replacing the output with the ground truth, and this speeds up training a lot, because now we can train everything in parallel without depending on the previous iterations. And this is one motivation for teacher forcing. So teacher forcing is this technique of replacing what the network is guessing to be the output with the actual output that we have in our labeled data. And in this particular case, for this particular network, this allows us to parallelize training and makes training much faster. Of course, even if it doesn't, even if we have, for example, a network like this, where we also have connections between the hidden states, in that case, using teacher forcing will not allow us to parallelize training, because we still need to know what was happening in the previous iterations. And this is actually a much more powerful network for learning good representations of the data. But even if in this case we cannot speed up training, but we can improve training by using the true value instead of the guess the network output is, which may be wrong. So teacher forcing in this kind of problems where we are training the network with supervised learning for some output at each iteration, and we have the output of the network feeding into the state at the next time step, then it's a good idea to replace the output of the network with the ground truth, because this will give us the maximum likelihood solution. So it improves convergence in training the network. Okay, so this is called teacher forcing, and it's useful in this particular case. But it also helps us understand one issue with recurrent networks, which is when we look at the advantage of parallelizing training in this way. So we no longer need to compute the previous iterations in order to compute what is happening at one iteration. In this case we would, because we would need to compute all of these previous outputs before, for example, computing the gradients of the loss function in this particular iteration. If we do teacher forcing, we can do all of these in parallel. So this would be great for speeding up training, but it also points out the problem that occurs in general with recurrent neural networks, that we cannot do this in parallel. So we need to wait for all the previous time steps in order to train the next one. So in general, training recurrent neural networks tends to be less efficient because we cannot parallelize as much as we can when we are dealing, for example, with convolution networks or transformers, etc. Okay, so during training, we do this in teacher forcing. We are replacing the output with the ground truth. Of course, when we pass for prediction, for inference, we no longer have the ground truth or the loss function. So in that case, we use the previous output to feed into the new state. And so we can now run our network like this. So teacher forcing, remember, only applies during training and not after the network is trained when we are doing inference. So another thing that we can do with recurrent neural networks, which makes things a bit more complicated conceptually, but can be very useful in sequences where the information is not only from one side to the other. For example, in time series, it should be only from the past to the future. It will not be useful to use data from the future to predict the past. But when you're looking, for example, at natural language processing, at text, then it may be useful to look ahead at what the words are further on in the sentence and use that information to make some decision on the other side. So in those cases, bidirectional networks can be useful. And here we can see a representation where we have the inputs feeding into these two hidden layers, F and G. Yes, F and B for forwards and backwards. And the forwards layer will influence the state in this direction, so going forwards in time, and the backwards layer is doing it the other way. So as we feed in this sequence, we have these states being influenced by the input and by the state at the previous time step, and these states here, B, the backwards one, are being influenced by the input and the state at the subsequent time step. So they are being influenced backwards through time. And then the outputs are a function of both hidden states here. You can do this in Keras easily using this bidirectional layer, which allows you to, which basically copies whatever recurrent layer you're using and reverses one of them. So it gives you this block here with the two directions automatically. Another thing that we can do is not for processing sequential data, so it's not the inputs that are in sequence, but we can use a single input to produce a sequence. And recurrent neural networks are good for that too. One example of those kinds of applications is image captioning, where we want the network to take an image as an input and generate a sequence of words that describe what is on the image. For example, black cat walking on grass, white cat walking on road. This kind of output that we want from the image means that the input into the network is just one input. It's not something that is changing over time, or it's not a sequence, but we want an output sequence from the network. So conceptually, we could imagine that we were doing something like this. We still have our recurrent network. It's outputting one value for each time step, but for each time step, we keep feeding the same input always. So this would be the image, for example. We keep feeding the image, and the network will output the first word, and then use that first word and the state as information to output the second word, and the third word, and so on. And we keep feeding always the same image as input, so that the network knows how to use the information for the image to guide the words that is generating. Of course, this is something that we can see conceptually. In practice, this is not a very good approach because it would require the network that we implement to receive the image as input and the previous word as input too. And this, for the implementation, can be a bit trickier. So actually, what is usually done is to use the information, the features extracted from the image, This is an example of a paper describing a method to create these captions. And the image is passed through a convolutional network that extracts a vector of features. And this vector of features is used to set the initial state of the network. So actually, the image will only determine what the initial state will be. And then from this initial state, the network will input a special start character that will lead to generate the first word from that initial state, and the initial state depends on the image. And then this word is used to feed into the next step. So basically, we are using only this part here, and the image only served to condition the first state of the recurrent network. So this is a more practical way, because now this part only uses the previous word until it outputs some special end word, and this lets the network generate the caption. For example, in this case, it would be straw hat, and then it terminates the caption, and the information from the image is just used to set the initial state. And all of these parameters are learned, how the parameters, the features from the image determine the initial state, and all the parameters for the transformations here inside the network. Another thing that we can do is, since we can use a recurrent neural network to pass either through one sequence into a sequence of the same length, or just using the final state or the final output. For example, we could transform a sequence of arbitrary length into a single vector of fixed length. We can create an encoder for any sequence. So if you imagine that we throw away everything except the last output here, we are only concerned about the last output, we can convert a sequence of arbitrary length into just this vector. So this would allow us to encode sequences of arbitrary length into a fixed representation, a fixed length representation. And since we can also use this fixed length representation to generate a sequence of arbitrary lengths, so this would be a conceptual way of doing this. We just keep feeding the same vector over and over until the network decides to end the sequence, or we could do it in a more practical way like this, where we use that vector to condition the initial state of the network and then just let it run to generate the sequence. But in any case, we have this ability of converting an arbitrary length sequence into a fixed length representation, and a fixed length representation into a sequence of arbitrary length. We can use these two recurrent neural networks to create this encoder-decoder architecture that can translate from sequences of some length into sequences of some other length. So this encoder-decoder recurrent neural network is very useful for things like converting speech to text, text to speech, doing translation, doing dialogues where you have a question and you need to generate the appropriate answer. Sorry. So all of these deal with sequences of different lengths. The sequences can even be in different modalities, text to sound, for example. As long as we have the appropriate encoder and decoder recurrent neural networks, we can fit the two together and do this conversion between one sequence and the other. And we can also do this if we want to obtain the same sequence in the output as we have in the input. We create a recurrent autoencoder. So the purpose here would be to generate those fixed length representations that we are using after the encoder for capturing the regularities in the family of sequences where these sequences may have different lengths. So we saw in the autoencoders that we saw previously, we can do this as long as we receive vectors that have the same dimensions. If we have sequences of varying length, then using encoder-decoder recurrent neural networks would be a solution, because then, independently of the length of the sequences, we can find the same length representation in the encoding. Okay, so let's see now how we can train these recurrent neural networks. We use backpropagation, of course, like we do usually, but now there is a tricky part here, because we are backpropagating something. Suppose that we have this input, our state keeps changing, and now we store this last state as the output. This is what we want. We have some loss function here, the ground truth, and so on. But now we need to backpropagate this through all the iterations we did. So the last value we have here, we measure the error, and we need to propagate the gradients of that error, that loss function, through these time steps. And the network state is changing over time. So if we do it like this simply, and we don't keep track of the different states, then we cannot backpropagate the gradients over time adequately. One way of solving this is just by imagining the network unfolded. So if we unfold the network, we can now easily propagate the error, whether we are looking just at the final output and the loss function here, or whether we are looking at the error at each output along the network. Independently of these architectures, if we unfold the network, then we just have a multi-layer network, and we can do backpropagation in the same way we did with general neural networks. So this is conceptually what we can do easily to backpropagate through time, is just to unfold the network, copy all the parameters. They are the same parameters. The state will change along the network, but now we have all these copies of the network unfolded through time, and so we keep track of all of these changes. And now we just do backpropagation. The only thing that we need to remember is that when we unfold the network, all of these parameters will be shared. So this W here is always the same matrix of parameters, the U is always the same U, and so on. So conceptually, backpropagating through time is trivial if we unfold the network and just do backpropagation as if we had a multi-layer network. However, in practice, this may not be very good, because you can do this in cache if you have an option in the recurrent networks to unroll the network, to unfold the network. And this can make training much faster, because once we unroll the network into a feed-forward graph, we now can use all the optimizations and the hardware and so on to train everything as if it was, for example, a multi-layer perceptron, and so it becomes much faster. But it's only good for short sequences, because remember, one advantage of recurrent neural networks is that we can have sequences of arbitrary length, and we are just reusing the same set of parameters and the same cell over and over here through time. If we unfold things and we have a very large sequence, then we will take a huge amount of memory, because we need the whole thing unrolled through time in memory. So this is not very good if you have large sequences, because then you can have a huge network in memory. So in practice, what Keras does is use this TensorFlow while loop. This is a symbolic loop where TensorFlow automatically keeps track of which things are changing and how to do the backpropagation over these steps. But since this will take these computations over time, it will iterate through all these computations, it's slower to train. Okay, so another problem that we have here in this kind of backpropagation is that we are applying the same transformation with the same parameters over and over again. So this is gives us that problem of vanishing or exploding gradients, which we had in deep neural networks, but it's a more serious problem in this case, because now we are applying always the same transformation, because we are reusing the same layer with the same parameters, and we are applying it over and over again. and this means that we cannot compensate the problem of one of them being shrinking, and then we change the parameters in the other layer so that it recovers the necessary information and so on. If we were training this as just a deep neural network, we could change these parameters independently and work things out better that way. With a recurrent network, we always have the same parameters. So basically, there is a small window there where we can keep things more or less stable, but if we deviate too far, the gradients will either explode or vanish as we keep concatenate, as we keep applying the same operations over and over again. So one alteration that we can do here to make training more efficient is to do the forward pass with a certain number of steps. So this will depend on the sequence that we are interested in. This would be the first parameter, K1. We feed forward all of these inputs, compute the changes in the state. But now when we are doing the backpropagation, since we are applying the gradients always to the same parameters as we backpropagate through time, we don't need to backpropagate so much as far as we did when we went forward. So it's important to use a sufficiently large window when moving forward because we may want to capture the history of what's happening over a sequence of inputs, but we may not need to go back as much when we are backpropagating the gradients through the parameters, because we keep revisiting the same parameters as we go back through time. So the idea of truncated backpropagation through time is to keep this number of steps when we do the forward pass as large as we need. It depends on the interesting part of the sequence, but then backpropagate through only a smaller number of steps so that we avoid revisiting the same parameters so much. We reduce the risk of exploding or vanishing gradients because we don't change them so much in the same pass and so on. Keras does not allow us to do this very explicitly, but because with Keras, if you set the size of the window, then for each batch it will pass your data in this number of time steps and then backpropagate the same number of time steps. So Keras will do this by default in each batch and then reset the state of the network for the next batch. So in that case, the number of steps we are passing through the network going forwards will be the same as we are doing in backpropagation. However, Keras has this stateful option where the state of the network is kept between batches, and we need to reset it explicitly at some point. So using this, we can use a smaller time window for training the network, and this time window will determine how many steps are backpropagated. But as long as we align our batches properly, our samples properly, we can keep the states of the network from one batch to the other, and so we are effectively feeding it longer sequences while changing the state along these longer sequences and just backpropagating through smaller sequences of time. So this is one way where we can do truncated backpropagation in Keras, and it's more efficient when we need to deal with longer sequences, because it's best not to propagate through so many time steps, as that would aggravate these problems of exploding gradients, vanishing gradients, and so on. There is also one hack that you can do, which is keeping the right order within the batches. Since the state only resets after a batch, but this is not a very elegant way of doing it, and it may be a bit problematic. So using this would be the most correct way, and we're going to see an example of this in the second lecture, which is to use the stateful mode of the recurrent networks, where the state is kept across batches, and we explicitly reset it when we are changing from one sequence to another. Okay, so now let's look at the problem of learning long-term dependencies. As we saw, we have this problem of the recurrent neural network being a composition of the same function applied to itself many times. Because since we are using the same layer, we are stacking the same layer many times with the same parameters. It's very hard to compensate problems when things start vanishing or when they start growing too large. So while a feed-forward network could compensate this by independently training the parameters at different layers, the recurrent neural network cannot do that. And this also means that dependencies tend to get exponentially weaker as the interval of time increases. So if there is some relation between the value at one time step and the value at the next time step, the network can easily keep track of that because this involves just a change from one state to the other. But if there is an important relation between one time step and another one, say 5 time steps ahead or something like that, this already passed through the composition of the same function several times, and so it's probably very much attenuated. When the network reaches this state, it can be very hard to remember what was going on so far behind in time. So this is a problem because the idea of recurrent neural networks is precisely to find these relations, these dependencies over time. And so it's important to be able to remember things sufficiently far behind in time so that these dependencies can be found, even if they are long-term dependencies. So some solutions for this could be to use skip connections. So imagine that we have also connections that skip several times steps. This could be one possible solution for this. We can have we can remove connections. So instead of just adding skip connections, we can replace short length connections with longer connections. So suppose that sometimes instead of using one connection from one type to the other, we would use connections at different time scales. So we could try to improve in this way how the network remembers things that occurred previously in time. Another thing that we're going to see used in these gated units is this idea of leaky units, which is basically keeping linear connections to the cell itself. So suppose that we have here a connection that took a linear transformation of the cell and fed it back into itself. The parameters here could learn how to improve memory over important things. So if there is something important to remember, it would reinforce that and keep feeding it back into the cell so that it would not forget that important part. So these are some things that are more or less obvious that we could do to try to improve the memory over long-term, over several time steps so that we can learn long-term dependencies. Another approach that is a bit stranger, but it actually works, is to use these reservoir methods. So imagine the problem here basically is that as we keep changing the state and training these parameters, we keep focusing too much on short-term dependencies because they are a lot more intense and forget the long-term dependencies. So one thing we could do is we don't train this part of the network. We only train whatever is going here for the outputs, for example, the weights for the outputs. Everything that is involved in this part, we don't train. And so this is the reservoir methods. We initialize the weights for transforming the inputs into the states of the network and the way the states of the network transform over time. And this can be a very complicated network with lots of parameters, but they are not trained. They are initialized at random with specific distributions that try to optimize how memory will persist over time in this network. And now the only thing that we train are the outputs from the states, are the weights from the state of the network to the output. And this can be just a simple linear classifier and so on. So you can imagine that we have a hugely complex network like this that was just initialized at random, and then we train a classifier to use data from these different states to predict something that we want to predict. And the idea is that even though this reservoir of hidden states is created at random, all the weights there for the state transitions and the transformation of the input into the state is random, they can be large enough that there are useful features being produced there over time that capture the long-term dependencies that we want. So with the proper initialization, with the right distribution to optimize the probability of having something useful there, we can then train an additional layer to extract the relevant features and do the prediction that we want. And that additional layer can be very simple, just, for example, a linear classifier or something like that. So this is an interesting solution. It steps out a bit of the kind of models that we are looking at here, because now we are just training a linear classifier. The actual network was just generated at random, but these reservoir methods can work pretty well in some applications, so it's a good idea to at least to have a notion that they exist and what they are. But what I'm going to focus on, because this is perhaps the more interesting part of the recurrent neural networks, are these gated units. So far we've been considering that this is some amorphous thing here. It's just characterized by these parameters that transform the hidden state from one state to the other, and so this can be just some linear combination, an activation function, something like that, and we have not been concerned about what is happening inside this. But we can actually create these cells with some well-designed structure to try to solve these problems and to optimize the way the recurrent network learns. And one example of this is the gated recurrent unit. And the idea of a gate here is some set of parameters, some linear transformation here that is then passed through a sigmoid activation. So we get something that varies between 0 and 1, and we can multiply this by one of the information flows that we are caring about. And this works as a gate, because if the sigmoid outputs a 0, it blocks the data that is coming through there. The value goes down to 0. If it outputs 1, then it uses that value in full. It doesn't change the value. So by multiplying the output of a sigmoid with some flow of data that is coming somewhere, we can create these gates that block or let the information pass. So in a gated recurrent unit, we have this update gate here, Z, that will determine how much we are going to pass from the previous state and the input into the future state or the output. So basically, this cell receives at each time step one value from the input sequence and the state or the output of the previous cell. So this is something analogous to this representation, where the state is the output that we want, for example, at the end, and it's also what is being fed into the next time step, and we are getting also the input of the sequence at each time step. So this is the general idea. So looking at a more abstract level, in the case of the gated recurrent unit, we have here this input, the x value at time step t, the previous state of the network, which was output into this one, and now we have here the output coming out of this cell. So the first gate, this update gate, will determine how much of the input and previous state will take part here, and how much we will use from just the previous state or this candidate state that we have on this branch. I'm going to talk a bit about it. But using this sigmoid transformation here, when we multiply here, we can block this value that is coming here if the sigmoid is 0, or we can let it pass if the sigmoid is 1. And this is 1 minus the sigmoid here, so we are doing the inverse on this side. This side is getting data from the input. This one is just passing the previous state. So this update gate will determine how much we are just copying from the previous state and how much we are changing based on the input. The reset gate will be used here to change the values for the input too, but it will based on the input. Note that these parameters, so these weights here that are multiplied by the input and the weights that are multiplied by the previous state, these are unique to each gate. So these weights are for the update gate. It will decide based on the vectors that are coming in the input and the previous state. And these are weights specific for the reset gate. And the reset gate will be used here when we use the previous state to try to compute what the next state should be. So if the reset gate gives us a value close to 0, the next state will ignore what the previous state was and depend only on the input. If the reset state is gate has an output close to 1, then the previous state will have a large influence on the current state here. So you see that we are actually designing this the inner part of this recurrent cell, this unit, in order to be able to fine-tune these different aspects. How much information we are using from the previous state, how much we are getting from the input. And so when we reach this part, the candidate state here, this will be given by the hyperbolic tangent. So this one goes from -1 to 1. And we can now use this as a function of this reset value that we have here, and also what we have from the x from the input. So the reset is giving us how much we should consider the previous state with some parameters that the candidate state can adjust here. These are learned parameters. And what we should do with the input, also with these learned parameters w. By the way, this operation here with the dot is just an element-wise multiplication. So these are vectors. So we have a vector here of values ranging from 0 to 1. We are using some weights for the vector of the previous state, but this reset gate is telling us to ignore some of them or to use others. So this one learned independently what to turn off and turn on from the vector of the previous activation. And this gives us a candidate for the next activation, but now that update gate will tell us how to use the new candidate and the old state. So this one is deciding how much we are going to feed into here, adding the new state, and how much we are just keeping from the old state. So one important thing here is that what is passing through from one state to the next is, you see this highway here is not subject to nonlinear transformations directly. We don't have any activation function here. These are just linear transformations, which are this multiplication and this sum for these update gates here. And so we avoid the vanishing gradients problem that occurs when we use those activations that saturate and the gradients tend to 0. We still can have the problem of exploding gradients because these things can go arbitrarily large, but at least the vanishing gradients is solved. And so these kinds of cells have less trouble remembering things that happened some time ago at previous time steps, because the gradients will not vanish. But we still have all these nonlinear transformations here to decide how to manipulate these values depending on the previous state, on the input, and so on. So this is one way in which the gated units, these GRUs, can help solve the problem of learning long-term dependencies. They avoid the vanishing gradients problem by having this highway of information with only linear transformations and no non-linear activations that would saturate, and all the non-linearity is being done here on the side and then added to the state. But in this case, these GRU are relatively simple in that the state and the output are the same thing. So you see what we get as an output from the unit is exactly what we are then inputting into the next one to recompute the state. Another kind of cell that is a bit more complex and a bit more powerful, this long short-term memory cell, uses not only this output here, which has a nonlinear activation, but it also keeps a state, this cell state, that only has linear transformations. So basically, this highway that we have here of nonlinear transformations is now the cell state, and it's not the output. And the output is also serves the output from the previous iteration is also fed into the LSTM cell, but now it's a different value, a different vector from the cell state. And this one has nonlinear transformations here. Okay, so let's look at the gates that we have here. In this case, we have this cell state that, just like the GRU, only suffers linear transformations. So basically what we are doing is we have this forget gate that is multiplied by the previous state and determines how much of the previous cell state we can ignore for computing the cell state now. And then we add this input gate with multiplied by the candidate cell state that will be now added here. So basically we have a similar mechanism as in the GRU to determine what to forget and what to put in on the next state, and the cell state is just subject to these linear transformations here. Again, this operation is an element-wise multiplication. So these gates will output vectors of values ranging from 0 to 1, and they are multiplied by the elements of the other vectors to determine which ones are used and which ones are ignored. Okay, so the forget gate, again, it's a gate, so it's a sigmoid activation, and it's similar to what we saw in the GRU. We have a set of parameters that are learned to transform the input, other parameters that are learned to transform this output from the previous iteration, and then a bias value there for the sigmoid activation. So all of these are learned parameters, and now we have a vector of values ranged from 0 and 1 that will be used here to close or open the different channels in the cell state that we have here. So this would be the forget gate on this branch here that will be used on this part to determine how much of the previous state we are going to reuse in the current iteration. Then we have the input gate. So the input gate here has this activation, and it will be also a function of the previous output of the inputs. But note that now the parameters for the input gate are just for the input gate. They are different parameters than the ones used in the forget gate. They are learned independently. But it's a similar gate, and it will be used here to determine how much of the candidate cell state will be fed into the current cell state. So this will be a function of the input and the previous output, and will determine how much information we get from the candidate cell state. And the candidate cell state will be this activation here, the hyperbolic tangent activation, and it will also be a function of the input and the previous state. But it has its own parameters, so this is learned independently. And basically we have here, to determine how much we are going to change the cell state, we have the forget gate, which allows us to forget, to put to zero some parts of the previous cell state. And then we have the input gate that allows us to select which parts of the candidate we're going to use, and the candidate is learned independently as a function of the hidden the output of the previous iteration and the input vector. And in this case, this one varies from -1 to 1. So note that when we are adding this into the cell state, we can be increasing or decreasing values in the cell state vector. So now we pass on to the current state. The current state, as we saw, is just multiplied by the forget one to remove some, and then adding the input gate and the candidate state to select which values we're going to add here. And the candidate state, since it has a hyperbolic tangent activation, can be from -1 to 1. So it can subtract some values or add some values depending on what the input gate decides to let through. Okay, so this tells us how the next cell state will be. And now we need the output gate. So the output gate will have this sigmoid activation here. And we will compute this output gate also as a function of the previous output of the cell and the input. It has its own parameters to learn, and it will determine how much of the cell state will be used for the output here in this current iteration. So again, it's a gate with the sigmoid activation. We have a vector of values from 0 to 1, and it can turn off or let through different parts of the vector that is coming from here. And this would be just the tangent activation over the hyperbolic tangent activation function over the current cell state, and then multiplied by this gate. This will determine what the output will be. So here we have a nonlinear activation applied to the cell state to get us the output of the cell, the current cell, but the cell state is not transformed by a nonlinear activation, so it doesn't suffer from those problems with the vanishing gradients and keeps flowing information into the next iteration. So LSTMs are widely used because of the way this design allows them to more easily learn long-term dependencies by keeping track of the relevant information in the history of the data that is flowing through this cell state. Because without these activation functions that saturate here, we are not losing much information, or we don't have this problem with the vanishing gradients in the flow of the cell state. Okay, so basically these gated units use these gates, these sigmoid activations that can use to cut parts of the vectors that are flowing in the unit. And they have this memory of the state. In the case of the GRU, this hidden state is also the output, and it has no activation functions to avoid saturation of the gradients. In the LSTM, it's a bit more complex. The output has an activation function, the hyperbolic tangent, but there is this cell state that only suffers linear transformation, so it helps the LSTM not so easily forget what was happening in the past. So these are the general ideas of the gated units, using these gates to control flow and using this highway of states that does not have a saturating activation function, so that it can avoid the vanishing gradients problem. Okay, so to sum up for this lecture, we saw the idea of unfolding the recurrent neural networks, and also as a way to understand backpropagation through time. So if we unfold the network, we get, instead of having a recurrent network, we get a feed-forward network with lots of copies of the same parameters along the different layers. We saw different architectures, so we can easily map from one sequence or sequences of varying length into a fixed length representation, or we can map from a fixed sequence into sequences of varying length, depending on the way we create the architecture of the recurrent neural network. And so we can also feed these together and create these encoder-decoder networks where we pass from sequences of some length into sequences of a different length, and this can help with problems like translation and text-to-speech and so on. We also have this problem of long-term dependencies, how we can learn things that are spread out over time when we keep using the same function over and over again as we iterate through the network. And so one solution is to use these gated recurrent neural networks that have both nonlinear transformations and a flow of information that only suffers linear transformation, so that it can better remember what was happening a longer time ago previously. So to read this in more detail, I recommend chapter 10 of the textbook. And that's it for this first lecture. Let's take a short break, and then the next lecture will be very short, just to show you how to do this in Keras. Because then in practice, as long as you understand the concepts and how these things work, putting them to work in practice is not very difficult. So the exercise will be easy today, and the second lecture will be short. So let's start again at 10:15 and take a almost 10 minutes break. See you soon.